Let me give you a little bit of history. This goes back to my years at University of Akron under Dr. Alan Gent and also Dr. Maurice Morton, who was the director then. I did ask them a question about how to characterize dynamic properties of rubber. This was way before what we now have in the market. At that time, I heard that Yearsley oscillograph was the characteristic dynamic tester of viscoelasticity of rubber. Viscoelasticity was just coming into play in this industry. So at that time, I did search for Yearsley and found out Dr. Felix Yearsley, who was employed by DuPont, and he designed and developed this oscillograph, mechanical oscillograph, and also had ASTM D945 test method implemented. And then I got in touch, found out Dr. Felix Yearsley unfortunately passed away. So we bought out the company's assets and carried on. During the years when Dr. Yearsley was producing this oscillograph, he sold it to well-known companies in the world. I mean, aeronautics, tire, NASA, and many others. So it was well established that this equipment could characterize the rubber properties at low frequency, but definitely at the time of testing, it could generate the natural frequency and all the parameters at that natural frequency. So as we carried on, we have developed a new model, which we call DMYO number 5. Our original model was AYO number 4. And DMYO number 5 is a bit different. Tavdico is a US corporation in Rhode Island, and we are an innovator and design and engineering company, basically producing very unique equipment for testing industry. This came along and we decided to add a few things to the original equipment, which we did. The DMYO-V now has a load cell, a displacement transducer, a very extensive software to evaluate its results. And I would like to discuss is on this slideshow, the unit is composed of a base and a beam, which is a balanced beam, and software. The unit has a traveling table that moves between 4 and 11 inches, 4 inches from the fulcrum to 11 inches from the fulcrum, with weights which can weigh 5 pounds each. And these weights can be up to 4. We can travel this table during the dynamic test and bring them to any point, so incrementally changing the moment of inertia of the equipment. As we change the moment of inertia of this equipment in dynamic testing, by the way, I should probably mention that the dynamic testing in compression mode and or shear mode are the two characteristic testing modes. The dynamic testing, and then we also do a hysteresis testing, and finally creep testing and the compression set test. So all these can be done on this equipment within short period of time. Dynamic testing can be between 3 and 5 seconds. Within 5 seconds, it depends on how elastic and how plastic the sample is. In other words, if the sample has high delta or loss angle, that can take a little longer, maybe 5-6 seconds. If it is an elastic product, within 3 seconds, 2 seconds, we obtain the natural frequency and all the parameters of that particular sample. So that being the case, as we can take a look on the lower left corner, the compression specimen, and the right corner, lower right corner, there is a shear specimen. So basically, this is how we move. Now, the next slide shows us the output that we generate from a test. The first thing I would like to refer to is the load versus displacement plot up on the right top corner. This specimen gives us quite an angle, quite an area under the plot, which shows that loss energy is substantial. As we go down to Jersey resilience, in this case, 16% definitely shows that it is not an elastic product, but more of a damping characteristics. The Jersey hysteresis is 83%. That is quite high, so loss energy is very high. As of course we move down to point modulus and dynamic modulus, and then of course the natural frequency 6.5%, 6.5 hertz, and that is a characteristic showing us its high natural frequency. Our natural frequency range goes from 0 to 20. We cannot go beyond that. And next is at that moment of inertia, which is calculated based on the beam moment of inertia, added on the weights and their moments of inertia to it. Then we go down to energy absorbed and power absorbed, and energy return and power return. There's a 10-to-1 ratio, as you can see. There's a lot of energy being absorbed because it's a damping characteristics, high damping characteristics. Next, we look down at loss energy tangent delta, which is 0.565, referring to a loss angle delta calculated on the basis of ASTM D5992. By the way, I would like to refer to D5992 characterizes dynamic testing systems under free oscillation and forced oscillation. Our system is a free oscillation system. The forced oscillation system is based on hydraulic, piezoelectric, or other actuators, which really can scan all the way up to a given hertz. And then it has to calculate natural frequency throughout that scan. In our case, our natural frequency comes out in 3 to 5 seconds, and that's what we are looking at. So with this 5992 test method, we do calculate the loss factor tangent delta and the angle delta. But on the other hand, we do log decrement, and we also measure phase angle. That's the difference between the two plots we have down below, which is the load and displacement against time. And that's 25 degrees, substantial. Now, tangent of phase angle is also given. Next, we go down to moment arm, which is a factor, of course. The measured force, which comes out of load cell. Final deflection, 52%. Dynamic point modulus ratio is also useful. Damping coefficient is. We also calculate E prime storage modulus, E double prime loss modulus, and E asterisk, which is the complex modulus out of those. This is for compression. We also report G prime, G double prime, and G asterisk for shear tests. Then we go to the next test, which is, sorry, okay, finally. Okay, this is called static hysteresis test, which really is, as we go back to the table, the moving table, we can initiate that motion. Say, between 0.1 inch and 1 inch increments, meaning the table moves and stops for a second or 5 seconds or whatever you choose. And then it takes a measurement. It carries on, moves another increment, the same increment, and takes another measurement. And that's more of a static testing. As it does that, it can do as many cycles as you want. Now, if we look at this plot, in this case, we have 3 cycles. The first cycle, and the second, and then the third. That's what we call is Mullins effect measurement. And in our report, as you can see below, at 20.7%, we do take a measurement of static modulus on the loading side, which is 4.882, and loading side is this side, and the unloading is along this line here. We do also report unloading static modulus at 9.24, almost twice. And energy loss per unit volume is also reported. Then we also report elastic region modulus. And below, we do refer to change in strain values at maximum strain, which we think is very important for compounding engineers and technicians to know a little bit about Mullins effect. So that being the case, we go to this plot, which is a multi-plot function. In this case, we have 4 different Shore values, 40 to 70, and each one has different slope, as we reported. The red, which is more elastic than the others, has a slope of 1.125 megapascals. So then comes green, which is 2.707 at 50 Shore A. Then comes blue, 3.5, and black at 4.8. These are different slopes. Actually, the slopes are taken in the linear region, meaning right about here. And these are the linear. And we relate this to crosslink density relatively measured. That's what we think is very important to be able to figure out. Not an absolute measurement, but a relative measurement. We go to the next slide. Here we have, as you can see, a loading curve in compression and showing an absorbed energy at loading. And then released energy at unloading. And hysteresis is the difference, of course. And as the material is more elastic, then that difference is much less. If it is more plastic or more damping, the difference is quite high. Last but not least, creep test. We also do that. And it is important to be able to measure creep for various end-use applications, such as O-rings, seals, and for example, if you think of seals and O-rings, certain applications such as sealing nuclear waste encapsulated in tanks or whatever with an O-ring, you don't want that to leak if there's an earthquake or something. Meaning, if there's a danger of leak, the O-ring has to recover within its capability as soon as possible, so the leak will be minimized. And there is the natural frequency characteristics and the dynamic properties come along very importantly. Of course, seismic construction, bridge, buildings, seismic waves can be low frequency waves and are very important to protect the buildings and construction. Yeah, isolation of machinery from ground noise is very important, especially if the machinery is highly precise and highly sensitive to such noise. And also, isolating ground from heavy machinery is as important. And that basically is our equipment. We'll be very happy to answer your questions or send you more information if you would like to. And I would like to show you a video at this point. If you would like to, please stay with us. I also would like to thank again for Technobiz for giving us this opportunity, and also the CEO, Param Rao, for giving us this opportunity. Thank you very much. Then we will start running a dynamic test, dynamic in compression. At this point, we shall go to the laptop and set our initialization. We initialize and set 0. Okay, it's set 0. Now we initialize, which is 4 inches from the fulcrum, and then we go back and fill in the dynamic test data. Hysteresis.
No, this is dynamic.
Okay. Okay, and the plot appears. There are 2 of them. One shows the load versus displacement against time, and the other one, the earlier one, shows load versus displacement. Then we have a tabulation of outputs, and this tabulation is where the data is critical. Just for example, we would like to point out the Yearsley resilience and its group underneath, which is common in D945-22, the latest version of the test method of ASTM. And then underneath there's another group of energy by integration of load cell, and the next one is loss factor and loss angle. The measured calculated loss angle in delta of 27 degrees and measured phase angle of 19.7 directly measured. Then we see moment arm, and then the complex modulus 641 psi. We have this output which we can use for dynamic tests, and then we can have a hysteresis test, which will be a test of static measurements. In a hysteresis test, onu kilitlemedin. Nuri. Boşta o.
It's okay. That's okay.
Okay. Okay. Okay, we have the data input which says minimum, the maximum moment arm 10 inches, the maximum strain 40%, maximum load 120 pound forces, pause at every step of 5 seconds, sample near between 0.1 and 1 inches, in this case quarter inch. Okay, at this point we change to 2 seconds, stop, and the hysteresis repeat is 2. The weights are 2 and each weighing 5 pounds. Once we do that, we go back to the table and start the test. As we initialize, the test starts. Moving table moves with weights on it and stops at every every half inch. When it hits the limit of 10 inches or 40% or 120 pound force strain, it reverses. What's important in hysteresis is loss of energy. As the specimen experiences compression forces, when the forces are reversed, some of the energy is wasted in viscous component, and the elastic component, of course, stays the same. However, it depends on the filler structure, the agglomerate, mixing, cross-linking structure of the final component, and how it behaves once it comes out of a mold. It is also important to know about this behavior as something called Mullin's effect, meaning if the component keeps experiencing repeated stresses, it softens up. How does it soften up? It softens up because agglomerates start breaking up, forming smaller agglomerates, and therefore voids are lost, so it becomes more dense. And but on the other hand, the cross-link structure, double bonds of carbon-carbon bonds are breaking up. As they do, the material softens up. So it's a matter of how this product has to live its life, and the engineers, the technicians of rubber compounding companies should know better how to formulate and vulcanize their products at what temperatures and what conditions. This is basically what we have as we go forward in these two tests. These are the compression tests. However, we also have the shear tests. The shear specimen is composed of 2 rubber components bonded to 3 steel platens, and the forces are perpendicular to the beam. So in this case we have a shear specimen which we will run a dynamic test on, and as we can see there are 2 weights on the traveling table, and that is ready to run now. The first plot is our load versus displacement plot, and it's very clear. And then the next one is against time, load displacement against time. Tabulation is on the right, and we see outputs from there as we did before. We shall run a creep test on this shear specimen, and same conditions as we did on the dynamic test, and we will allow 60 seconds for the creep test, and we are setting up, ready to go, and go. And once the creep starts, plot collapses towards left, and displacement shows that if the creep is actually happening, which we can see a little bit here, as you can see, as the seconds move, the bar graph at the bottom shows the time function. Creep is very important for products that go into constant strain, constant stress situation under weight, such as heavy loads, seals, and anything that seals a product from ambient conditions has to be designed for good creep properties. At this point, we have to measure the compression set and include that in this calculation. And the dial here gives us the compression set measurements. Okay, thank you.
Okay, thank you, Dr. Ismail. Would you like to add any final remarks on your presentation?
Thank you, Param. We appreciate your inclusion of us in this very fine webinar. We thank you for that. We also thank the audience for their attention. We're ready to answer questions. We're ready to run tests on some samples if anyone chooses to send us samples, basically as per D945-22 specs. Other than that, we thank you again, and we hope to be at another one of these webinar sessions in the future. Thank you, Pero.